Hello guys, so we are going to continue the discussion with respect to derivatives. Already, if you remember, if in the previous video, I've already spoken about how do you specifically calculate a slope, right? Let's say if there is a line, slope is nothing but it is talking about the rate of change with respect to x, right? With respect to one variable to the other variable, right? So if I have x over here, I can actually call this as delta x it should be. Okay, I can call this as delta x and this is my delta y. When I say delta y, this is nothing but y2 minus y1 and this is nothing but x2 minus x1, right? So in short, if I really want to go ahead and compute my slope, it is nothing but delta y by delta x. Okay, here for every point, for any point, since this is a straight line, the slope is going to be same, it is not going to change, right? But in most of the scenarios when we specifically work in differential calculus, right? Let's say, okay, in this scenario, I can consider this line as this equation, y is equal to mx plus c. And with the help of this equation, we get a straight line, right? Straight line. Perfect. Now let's consider that instead of like this, right? We have a different kind of curve like this. Let's consider that we have a curve like this, and this curve is denoted by a line or by this equation, which is called as y is equal to f of x. Okay, let's just consider this. Okay, so there is some curve, and I'm just denoting this entire line by y is equal to f of x. Now in this scenario, here you will be observing one very important thing. Let's consider every data point. Let's say I want to understand what is the slope between this point to this point, right? So here you'll be able to see that there is some slope, right? And when you go forward, here again the slope is changing. Here the slope is increasing. Here the slope is still much higher. So here, if I probably consider the average slope, right, it is changing each and every time because this line is completely non-linear, right? Or it is a curve, right? This is one of the very unique property that you'll be able to see. Now, obviously, if you ask me, Krish, what is the average instantaneous rate of change with respect to this x and y coordinate? I can calculate this. See, if there is a question like, hey, you'll ask me, Krish, what is the average instantaneous rate of change with respect to x and y, right? So what I can do is that I can consider two coordinates, and what I will do for this coordinates, I will go ahead and just find out the slope. Now, in order to find out the slope, what I'll do is that I will just go ahead and create a straight line. Okay, I'll create this straight line. Let's consider that this straight line is passing through this coordinate, right? Now, this line is basically called as a secant line. Secant line, right? Now, when this straight line is basically passing through these two coordinates, I'm just drawing this line. Now, if I try to calculate the slope of this line, the slope of this line can be calculated. You know that, right? Let's say that if this is my coordinate x1, y1, this can be my coordinate x2, y2. I can go ahead and calculate it because I have actually drawn a secant line, right? And for this, I will use the same formula. The formula will be nothing but slope is equal to delta y by delta x, right? But my scenario is that, hey, what if I just want to find out with respect to this x value or x1 value, right? What is the rate of change with respect to y? I want to find out this specific value, right? For this x1 value, what is the instantaneous change with respect to y? But in this scenario, obviously I cannot draw the secant line because to draw the secant line, I require two coordinates. So usually what happens is that this can also be solved. And for this, you need to draw a tangent line onto this particular point. When you draw a tangent line and then you go ahead and calculate the slope of the tangent line. When you go ahead and calculate the slope of the tangent line, because when we draw a tangent line which is passing through this particular point, through this particular coordinate of x1, right? Then obviously you can calculate the slope of this, right? And once you calculate the slope of this, which is passing through this particular point, then you can talk about what is, or you can basically showcase what is the instantaneous rate of change of x with respect to y, right? With respect to y. Now, usually in a straight line, we can calculate the slope by, as I said, right, by probably just seeing the two coordinates, because the slope is going to be constant, or it is going to be same for all the data points over here. But whenever we have this curved line, we cannot just directly use slope. Instead, what we do is that for whatever point we specifically want the instantaneous rate of change, we go and draw a tangent line. This is my tangent line. And then we go ahead and calculate the slope. And this will in turn give me the instantaneous rate of change of x with respect to y. Now, if I really want to go ahead and probably find out the slope of this tangent line, here we basically denote this by dy by dx. So this is how the slope will get calculated. Now, this dy by dx is nothing but it is called as derivative. Okay, please understand this. What is this dy by dx? I will just talk about in some time. But just for right now, I'm just putting this notation, so this notation is there in your mind, right? So if I really want to calculate the slope of a tangent of a line at any point, I have to use this particular formula to calculate it. Okay. Now let's do one more thing. Okay, let's draw the same diagram over here. Let's say that I have a curve. Okay, let's say I have a curve which looks like this. Okay, and now my main aim is basically to calculate the slope at this particular point. So I've drawn a tangent line. So this is my tangent line. Okay. As I said, one way is that if I want to find out the average instantaneous rate, what I will do, I will probably draw a secant line, right? I will draw a secant line like this. This will be my secant line. So once I draw a secant line, I will be able to calculate the slope. Now, if you really want to understand about this tangent line and calculating the instantaneous rate of change with respect to this particular point, that basically means what? For this x value, we are trying to calculate the f of x, right? What is my f of x? If I consider this is my f of x and this is my x coordinate, right? But understand with respect to secant line also, we can come over here. We can come to this specific location, right? So initially we had this coordinate, right? This far the coordinate. What happens if I probably move the coordinate over here? If I move the coordinate over here. So for this coordinate, I can draw another secant line, right? The another secant line may look something like this, which if we connect these two dots, so this can be again connected. Or let me just use another color. If I connect these two dots, it can be connected, right? Similarly, if I move this coordinate points more towards near to this particular first coordinate, let's say I'm moving over here now. And similarly, I'm moving over here. As I move towards this point, finally, you'll be able to see that I will be able to get this instantaneous rate of change for this particular point. Because see, when we are decreasing the distance of these two coordinates, where it is coming to this particular point, right? And that is how we can go ahead and probably compute the slope with respect to that particular point. Initially, I had a secant line, but as I went and probably used different points, okay? If you probably want to see this in much more clear graph, I will just go ahead and make this, okay? Let's say this is my curve. Let's consider this is my curve, so, right? Now, initially what happened, I was trying to compute this. So let's say this is my 2 points, right? 2 coordinates. My main aim is basically to compute the slope at this particular point, right? At this particular point. Now, to calculate the average instantaneous rate with the help of secant line basically means I will just go ahead and connect these 2 dots. And this is my first dot that I'm actually getting. And I will just go ahead and compute the slope. For this, the computation is very easy. If I want to come from these 2 points to a single point, what I can do? I can move my coordinate nearer to this point, right? Nearer to this point. And for every point, I can go ahead and construct my secant line, right? And then I can also calculate the slope. But what if this red point meets this orange point, right? As I move towards this point, right? what happens over here? See, this point is basically denoted as, let's say this point is denoted as, here I can write this, if this is my x coordinate and f of x coordinate, okay? This is nothing but x comma f of x, okay? X comma f of x. F of x basically means this particular value. What about this point? Let's say that this is my x1. Let's say here I'm going to write it my x1 and this is my x2, right? So similarly, for this particular point, if I go ahead and see with respect to this coordinate, this is nothing but x2 comma f of x. Now what I am actually doing is that my x2 will probably go towards x1. When it is going towards x1, that basically means this distance is decreasing. And finally, when this entire point comes over here and gets overlapped, let's consider that it is getting overlapped. Now here I will get a single point and then I will be able to calculate the tangent of this specific line, right? And this is what, this is specifically called as limits, and that is where your limits will come into introduction. Okay. Now what does specifically limits specify over here, right? We'll discuss more about it. We'll go ahead with understanding the equation. I will be using these equations and all, right? But our main aim over here is that how from a secant line, we can probably come to a single point of line and calculate the tangent or get the tangent and then calculate the slope. Because once we get this tangent, we will definitely be able to calculate the slope, right? So initially I had a secant line, okay? Then for every coordinates, now we are moving towards this. When we are moving towards this, right? See, for this coordinate also, I can go ahead and probably create my another secant line, which looks like this. Then it will come another secant line. Then we can calculate the slope. Then we can calculate the slope. Then we can calculate the slope. But once it gets overlapped, we will only get a single tangent line. Okay. And this is the concept of limits, which I am actually going to discuss in the next video. But I hope you got an idea with respect to all the notation that we use. And this point, in a single point, when we draw a tangent and once we compute this slope, this is nothing but we are trying to find out the derivative with respect to this particular point of the f of x. Okay? Of the f of x. That is the reason we have written dy by dx. This is what derivative symbol is basically there. What exactly is derivative and how do we come to this particular conclusion? I will be discussing that in the upcoming video. But I hope you got an idea with respect to derivative as a concept. For a single line, the slope calculation is very simple, right? But if you have a curve, if you have a slope, if you have a curvy line, if you have a non-linear line, for every data points, there is a change in slope. Right, the rate of change, the instantaneous rate of change is basically different, right? For one of the point, it may be less, for other point, it may be more, right? So that is what I'm actually going to cover in the next video, where we will be talking more about limits and we will be also equating with respect to some equations, right? So yes, this was it from my side. I will see you all in the next video. Thank you.